So, hello my dear students, my name is Benatang Paton and I welcome you to the channel Classroom where we learn together. So today I have a very important experiment to discuss with you. Our topic today will be Oersted's experiment. This experiment is there in your textbook. And this is a very important experiment, so we need to discuss this. So we'll start our class by explaining and learning what this experiment, which was performed by Oersted, is all about. Okay, so without wasting time, let's start our discussion. So Oersted's experiment, this was demonstrated by a very famous Danish scientist whose full name is Hans Christian Oersted. So let me write down the full name of the scientist, Hans Christian Oersted. This is the full name of the scientist, Hans Christian Oersted. Now, he was a Danish person and he was a physicist. Okay, a physicist is a person who studies physics. Now, as per the story, in the year 1820, he was supposed to give a lecture. So in the course of his lecture, he had to do a demonstration also. And his demonstration involved the use of a copper wire where he had to pass current. So let's say this is the copper wire. So this is the copper wire where he had to pass current. And placed on his table was a magnetic compass. So on his table there was a magnetic compass which was placed quite near to the wire. So since this experiment required passing of current, so he demonstrated his experiment. So he made current pass through the wire. So let's make current pass through the wire. So let me make a switch here. So this is a switch. Okay, so this is the switch. If the black dot is present, that means the key is inserted, meaning current flow will take place. So the switch is inserted, that means current flow is taking place. So current flow is taking place. So when current passed through the wire, when current flowed through this conductor, through this copper wire, Oersted observed a deflection in the magnetic needle. So the needle from its usual place, from its usual point, okay, it deflected like this. So this caught the attention of Oersted. So this caught the attention of Oersted, and Oersted wanted to know. Okay, so what he did was that he took out the key. So the key was taken out. So when the key was taken out, current flow in the wire stopped. So the current flow in the wire stopped. So current flow in the wire stopped. So let me draw the wire here. So this is the wire without the current. Without the current. And then what happened to the magnetic needle? Did the magnetic needle remain like this? No, my dear students, no. The needle went back to its default original position. So this is what he observed when no current flow took place in the wire. Then again, he inserted the key and then he made current pass through. So current passed through. Okay, let me use I. So current passed through the wire, and then when current passed through the wire, again the needle showed deflection. So this is what Hans Christian Oersted so in this experiment. So this caught the attention of Oersted, and then he tried to reason. Now, being a physicist and being a person of knowledge, being a person of great knowledge, he came to the understanding that the flow of current in the wire, the flow of current in the wire must have produced something, which made the magnetic needle deflect. I repeat, he came to the understanding that the flow of current in the wire, is the current not flowing in the wire? Yes, there is current flow in the wire. So he came to the understanding that the flow of current in the wire must have produced something in the wire, which made the magnetic needle undergo deflection. I hope you are clear. Okay, so this is what he came to understand. Now let me tell you what actually, okay, now a lot of time has passed, okay, when when Oersted first did the experiment. This was the first time that anybody, okay, nobody before him had ever recorded this experiment. So nobody was there to explain to him what it was. He was the first person to witness it. But okay, he did, okay, his understanding was so correct that he came to the understanding that something must have produced in the current carrying wire, which must have interacted with the magnetic needle, and what he understood was correct. Okay, today we know, okay, that what actually happened. Today we know what actually happened here. So what actually happened here, let me tell you. So what actually happened here was that the flow of current, okay, when current passed through this wire, magnetic field was created in the wire. So this magnetic field interacted with the magnetism of the magnetic needle, because of which the needle is showing deflection. I repeat, when current passes through the wire, the flow of current produces magnetism in this wire. So the magnetic needle, okay, has its own magnetic field. The flow of current is producing magnetic field in this current carrying wire. So this magnetic field interacts with the magnetic field of the magnetic compass, and thereby the magnetic compass is showing deflection. So this is what is actually happening. Okay. So now coming back to Oersted. So Oersted concluded that. So Oersted concluded that there is a relationship between electricity and magnetism. So this is what Hans Christian Oersted concluded, okay, and it is true. There is a relationship between electricity and magnetism, okay, and this relationship is what is called electromagnetism, and the relationship is what we call electromagnetism. All right, this is now a new branch in science, okay, and we study this. The relationship between electricity and magnetism has got a new name. Together we call it as electromagnetism. Before Oersted did this experiment, okay, people had a strong belief that current and magnetism had no relationship. Current was black, then magnetism was white. That was a relationship. That was how people believed, okay. But after Oersted did this experiment, now the understanding changed, okay. Scientists now, okay, they found that there is actually a relationship between current and magnetism, which is now we call it as electromagnetism. So I hope, my dear students, that this experiment is clear, okay. This experiment is mentioned in your textbook, and so I felt the need, and it is important to understand the experiment. So now let's move to the next topic. Let's learn more about magnetism. So remember, my dear students, when current flows through a wire, okay, the flow of current produces magnetism in the wire, and this, okay, was confirmed by none other than Hans Christian Oersted all the way back in the year 1820, and today we are in the year 2025, and see how applicable and how important, okay, what a wonderful discovery this was, okay. So let's continue with our discussion now with the next topic. Let's learn more about magnetism. Now, magnetism magnetism, M-A-G-N-E-T-I-S-M. Now, I want to tell you, my dear students, that magnetism, okay, is of two types. We can study magnetism under two types. We have permanent magnetism and we also have temporary magnetism. Now, what are these? Let us first start with permanent magnetism. Permanent magnetism means magnetism which does not change, okay, which remains fixed throughout time. For example, we have the Earth's magnetism, okay. So we have the Earth's magnetism. Earth's magnetism. What do you think, my dear students, that the Earth's magnetism, that the Earth will, that we will lose the Earth's magnetism? No. Remember, we will never lose the Earth's magnetism. As long as the Earth exists, the Earth's magnetism will remain. So the Earth's magnetism is permanent. So under permanent magnetism, we have the Earth's magnetism. Then the different magnets that we have, the bar magnets, the horseshoe magnets, the magnetic compass, all of these, they also fall under permanent magnetism. So we have the bar magnet, the horseshoe magnet. My spelling of horse, S-O-H-O-R-S-H-E. I was about to write this. Horse, okay, horse. Okay, it should be horse, but then these days I'm writing horse. So it's horseshoe magnet. My spelling errors are getting worse and worse each day. So horseshoe magnet. Then we have a magnetic needle. Magnetic needle. So these are examples of permanent magnet. Then we have one more, and that is magnetic iron ores, okay, Fe, which is iron only. So magnetic iron ores. So these are all, okay, all of these substances, they possess permanent magnetism. That means their magnetism doesn't change, okay. Their magnetism is fixed, okay. Their magnetism is permanently fixed. That means they will always exhibit magnetism. Now let's move to the temporary magnetism. As the name suggests, temporary, that means their magnetism is temporary, which means it will only be for a short amount of time. Okay, so let's learn about temporary magnetism. What are they? So we have number A, moving charge. Moving charge. Now we know what charges are. Okay, so we know what charges are. A charge can be a positive, a charge can be a negative. Yes or no? Okay, there are only two types of charges. It can be a positive charge or it can be a negative charge. Positive charge is given by a proton. Negative charge is carried by who? My dear students, can anybody tell me who gives the negative charge? Yes, you are absolutely correct. It is given by the electron. Okay, we have learned this in the previous chapter, electricity. So a moving charge. Now these are two charges, but look at what I wrote. Moving. They have to move. Only a moving charge will produce magnetism. Okay, if the charge remains stationary, remember, there is no magnetism. Very, very important. This has been asked, okay, in MCQ also, that which of the following produces magnetism, a moving charge or a non-moving charge? Remember, it is a moving charge which produces magnetism, and non-moving charge does not produce magnetism. It has to be a moving charge. So the charge has to move, okay? So a moving charge. So the charge is to move, and when the charge moves, they generate magnetic fields. So these are magnetic fields. So a moving charge generates magnetic fields. Remember this. Now these are permanent, these are temporary magnets only, okay? So as long as the charge is moving, magnetic field will be generated. When the charge stops, the magnetism will die. So that's why these are temporary magnets, okay? Then number B, we have current carrying wire. It can be a wire, it can be a loop, or it can be a solenoid. We will be learning about this in the upcoming videos. A current carrying wire. So current, this is a wire and this is the direction of current. Then a current carrying wire generates magnetic field, okay, around it. Then a current carrying loop means a wire, circular wire, okay. Then a current carrying wire also generates magnetic field. So the magnetic field will be like this, okay. It will be like this. We'll be discussing in detail about this in the upcoming videos. And even solenoid, a very, very important topic in your syllabus, which we will be studying in detail, okay. So a solenoid is like this, a coil, a copper coil having many turns, okay. Then we know that it also generates magnetic field. So all of this, okay, these are all, okay, which produces temporary magnetic field. I hope it's clear. So let's erase this and then let's continue further with our discussion. Now, earlier we have discussed about Oersted experiment, and there we noticed that the magnetic needle showed a deflection. So let's learn how to find the direction of deflection in the needle when it is brought near a current carrying wire, okay. Now, so there's a famous rule called snow rule. So let's learn about snow rule. Now this is not there in your syllabus, but then I strongly believe that this understanding should be there, okay. So it is being taught in the CBSE, so it is also important, okay. So even NBSE students, even you and I, we should know, okay. So this is important. This will help you determine accurately in which direction the needle will deflect, okay. Will it deflect this side or will it deflect this side? So we have to know that. So it's a very simple rule, okay. So let's learn this. So let me draw a wire here. So this is the wire and current is flowing upwards, and here I have the magnetic needle, okay. Currently it's pointing towards north. Now let's say current is flowing from south to north. So the direction of current is south to north. Direction of current flow in the wire is equal to from south to north. So current is flowing from south to north. Remember the cardinal points: north, east, west, south. So current is flowing from south to north, okay. So if current is flowing from south to north, then in which direction? Now the magnetic needle is pointing in the north direction, because that's what the needle is supposed to. It should always point in the north direction, okay, of the place from where it is being held. So it is pointing in the north direction. North is here, so the needle is pointing in this direction, indicating the north. Now current is flowing through this wire. So we know that from Oersted experiment that there will be a deflection in the needle, because this current carrying wire will produce magnetic field. So the two magnetic fields will interact. So the question is, in which direction will it deflect? The answer is it will deflect towards west, okay. So it will deflect towards west. Remember this, it will deflect towards west. So direction of deflection west. Now This I know because I understood snow rule. So what is this snow rule? Let me dissect it for you. Okay, so snow rule says that if the direction of flow of current is from south to north, snow rule states that if the direction of flow of current is from south to north, then the deflection will take place in the west. Okay, so what is the role of zero? I don't know. Okay, it's there because if it is not there, then it will be S and W. So it will be difficult for anybody to remember. It's not S and W rule. So to make it easier, let's just put O and make it snow. Okay, so that we don't forget. So snow rule tells you, okay, helps us to find the direction of deflection. So this is a very important rule. So current is flowing from south to north, then the direction of deflection will be towards west. So it will deflect towards west. So deflection will be from this to this. Okay, from this to this. This is very helpful. Now you go and check the diagrams drawn in the textbook, and you will know that they are also following this rule. Though they did not mention, but this is a very important off the topic, okay, off the textbook topic, which will help you draw accurately and understand accurately, okay, how to determine the direction of deflection. So very, very important. Okay, now let's further continue. Now we'll talk about a very important rule, which is Maxwell's right hand rule. So Maxwell's right hand rule. What is this Maxwell's right hand rule? There's a statement. First, let's write the statement and then we will discuss. So the statement goes like this. If the thumb points in the direction of current, if the thumb points in the direction of current, then the direction of the curl, of the forefingers, then the direction of the curl of the forefingers will indicate the direction of magnetic field. So this is a very, very important rule, which is called the Maxwell's right hand thumb rule. I wrote Maxwell's right hand rule. I think, is it Maxwell's right hand thumb rule or Maxwell's right hand rule? I think they are both same only. Okay, it's Maxwell's right hand rule. Sometimes we also call it as Maxwell's right hand thumb rule. So I think both are correct. Okay, so it's called Maxwell's right hand rule also, but since we are using the thumb, okay, it can also be called as Maxwell's right hand thumb rule. Maxwell's right hand thumb rule. So the word thumb should be there. Maxwell's right hand. It should be written here. Where am I writing? So it should be written here, not here. Galti ho gaya re baba. So right hand thumb rule. It should be right hand thumb rule. Okay. So the rule is Maxwell's right hand thumb rule. Why? Because we are going to use our thumb. So let us understand in detail this Maxwell's right hand thumb rule. So I have a scale here, and this will act as the wire, okay, where current will be flowing. So first of all, let's say that the current is flowing, okay, let's say the current is flowing upwards. So the direction of current is upwards. I stands for current, and the current is going upwards. So let this be the current carrying wire, and the current is flowing upwards towards the ceiling. All right, my dear students, towards the ceiling. So as according to the statement, my thumb should point in the direction of current. So should I be holding like this, or should I be holding like this? I should be holding like this. So my thumb should point towards the ceiling, because current is going towards the ceiling, okay, towards the ceiling. Current is going like this. So my thumb should point in the direction of current. So this is the right orientation. So let me hold it like this. So this is the right orientation to hold. So this is the right way to hold. Then the statement says, the rule says, now check out the direction of curl of my four fingers. 1, 2, 3, 4. These four fingers. 1, 2, 3, 4. The direction of curl of my four fingers. So the thumb is pointing in the direction of current, which is towards the ceiling. So it's correct. Now the direction of curl of my four fingers. Look at the curl. See, they are going like this, not inwards. See, they are going inwards. So let's keep it here. Then the thumb is already correct. Now see, it's touching the whiteboard. That means it's going inwards. Okay, so it's going inwards. So the direction of the curl. So the four fingers are curling inwards. Okay, they are curling inwards. So the direction of the curl of the four fingers will give the direction of magnetic field. So the direction of magnetic field is this. It's given by these four fingers. The direction of the curl of the four fingers will give you the direction of the magnetic field. So if I were to draw, how will I draw? I will be drawing it like this. So this is this circular, these concentric circles. These are the direction of the magnetic field in this current carrying conductor, where the direction of current is upwards. Okay, so they are going like this. They are going like this, is not? They are going like, they are going inside. So arrows will be drawn like this, and then they are going inside and they are exiting. So they are going inside. You see, they are going inside, and then they are coming out like this. No? They are coming out like this. So they are coming like this. So the drive has to be okay. This may be confusing, but this should not confuse you. So again, okay, make sure that okay, it's not confusing. Okay, rewind the video and watch again and again. It should not be confusing. So once again, current is going upwards. So my thumb is already in the right proportion. Look at how my four fingers will drive. So look, see how they are driving inside, isn't it? So let me show you from this perspective. So they're going like this. See, they're driving inside. They're going inside. So they are going inside. They're going inside. That's why the arrow is inside. It's going inside. Then after driving in, they're coming out. They're coming out. So the arrow is pointed outside. All right, because the magnetic field lines. Okay, because it has to be concentric circles. All right. Then next, what if the current is flowing downwards? Then now the current is flowing downwards towards the floor. So this is the same conductor. Previously current was going upwards, but now current has changed the direction. So now current is going downwards. Current is going downwards. So how do I hold my thumb? My thumb has to always point in the direction of current. So now this is the right way. Okay, this is the right orientation for my thumb. My thumb should point in the direction of current flow. So current is going down, my thumb direction also is down. So this is the right position. Okay, now look at the curl, look at the drive. Okay, look at the curl of my four fingers. See, it's not, it's coming towards you now. It's coming towards you. It's coming towards you. So the magnetic fields, they will again be circular. Okay, this will be circular rings. Okay, so here also it will be circular. Okay, and look at the drive. Look at the drive. See, it's coming towards you. It's coming towards you and it's going inside. So it's coming towards you. So if I do like this, if I do like this, so if I hold it like this, if I hold it like this, then they're entering from this side. They're entering from this side. So it's entering from this side and it's coming all the way from this side. Okay, see, it's entering from here. Okay, it's entering from this side and it will come out from here. So entering from this side and coming out from here. So they're entering from this end, they're entering from this end, and they're coming out from here. All right, so this, my dear students, is how you determine the direction of, how you can determine the direction of magnetic field, provided you know the direction in which current is flowing. Okay, so I know many students are confused. Okay, many students find this how to find the direction very confusing, but believe me, okay, it's easy. So it's very easy. Just what you have to do is align your thumb in the direction of current. Then all you have to do is, so the current is going up, so the marker should be held like this. My thumb also should be in the direction of current is going up. Then the curl of my fingers, okay, this will make circles. This is the direction of magnetic field. Okay, and then if the current is going down, okay, then my thumb will also go down, and this, the direction of movement of my forefingers, will indicate the direction of magnetic field. So the magnetic field will be circular again, and I can even know the drive also. So it's going like this. Okay, it's going like this. So it enters from this end and it comes out from this end. Okay, so this may require some practice, but I am very sure, and I assure you that you will get it. Okay, you will get it. You'll get it. So this is it, my dear students. I'll end the video from here. It was a short video. Okay, it is a short video, but then, okay, this is a very important video. So in this video we have talked about Oersted experiment, and then a small rule called the snow rule, and finally a very big topic, which is Maxwell's right hand thumb rule, which is very, very crucial, okay, for each of you to understand. With this understanding, you will be able to understand better the next topic, which is direction of magnetic field on a straight current carrying wire, followed by direction of magnetic field in a circular loop. So I'll end my video from here, and I thank you all for tuning in and watching, and I'll see you in the next video.